So just only 11 people are there. So just to let you guys know that there will be no leniency in attendance, and I have to mark the attendance in the first 10 minutes of the class. So if anyone is coming or wants to join the class, he or she should be coming very quickly and not delay too much, so that their attendance does not go out of control and their course do not is not dropped. Okay. So I will go through the attendance first. Um, in the attendance, we have this is 5B. So we have go through the summary of the attendance. So we have over here we have Usman Akmal. Uh, his attendance is fine, and I'm going to give the name of those students whose attendance are going getting below the certain threshold, right? So Bisma Salim, uh, she is in 70s. I mean, if she is absent few more times, then her attendance will go beyond the threshold level. Adil Umar, he needs to be very careful about his attendance. He has very less chance. He has 11 absences already, and I won't be able to mark attendance of anyone who comes at the end of the class. I mean, you have to be here at the start of the class, right? And then we have Muhammad Umair, Iram Shokat, Safan Ahmad Ishaq. We have Khizar Akram, Zainab Umair, Tahir Hamid, Shamrez Tasawwur, and Hassan Asif. Hassan Asif is Shamrez and Hassan Asif are very at the very edge of the issue, and I can't mark anyone's attendance. Fazur Rahman is also
Present,
in
sir. Yes,
70s,
present.
and Hassan Faisal and Ibtisam Abid, they are also in a very marginal. They're at the margins of the attendance, so they should be very careful about their attendance. So I have a few of your comments over here. So I'm going to take attendance now. I haven't taken attendance until now. So you should mark. You should call present or absent whenever I call for attendance. Right. Right now, I'm just discussing your previous summary of attendance. Okay. So coming to the. So we have. We have 2 hours attendance. These are routing protocols. Okay. So now I'm going to ask for attendance. Usman Akmal. Usman Akmal is present.
Present.
Okay. Umair Latif.
Present.
Umair Latif is present. Muhammad Taha. Muhammad Taha is not present in class, right? Muhammad Taha Rao. Okay, he's present. Wajiha Noor. Wajiha Noor is present. Wajiha Noor, are you present in class? Okay. So why are you not speaking in your mic? Is there any issue with your mic? Osama bin Tariq. Osama bin Tariq. Israr Ayub Bajwa.
Present, sir. Present.
Present. Muqaddas Fatma.
Present.
Ghayur Abbas. Ghayur Abbas is not present. सो मुगीस अली, सैयद मुगीस अली।
Present, sir.
सैयद मुगीस अली। सो आई डोंट नो इफ आई मीन आप किस नाम से हैं?
Enrollment, sir, 017.
अच्छा, मुगीस अली प्रेजेंट। बिस्मा सलीम। बिस्मा सलीम। बिस्मा सलीम इज एब्सेंट। ओके। अली हसन आजाद।
प्रेजेंट सर।
अली हसन आजाद इज, आप भी एनरोलमेंट से नंबर से हैं? अच्छा।
नाम भी लिखा है सर।
वहाँ ब्रैकेट्स में लिखा हुआ है। अच्छा, मोहम्मद अदील उमर।
प्रेजेंट सर।
ओके। ताहा इफ्तिखार।
प्रेजेंट सर।
मोहम्मद उमैर।
प्रेजेंट सर।
इरम शौकत। इरम शौकत प्रेजेंट। आपका माइक नहीं चल रहा बेटा, तो इसका आप हल निकाले ना, क्योंकि आप तो हर हर वेडनेसडे को, अब हर क्लास सेमेस्टर 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 के वेडनेसडे को अब ऑनलाइन क्लास हो रही है। तो यू शुड बी प्रिपेयर्ड फॉर द ऑनलाइन क्लास। आपके कोई सवाल पूछे, सवाल क्लास में तो कैसे आप जवाब देंगी? अच्छा, अब्दुल वहाब। अब्दुल वहाब एब्सेंट है। सफ़ान अहमद इसहाक।
प्रेजेंट सर। प्रेजेंट।
सबा सबा अनवर।
Present.
ओके, मीर हमजा।
प्रेजेंट।
हमजा खालिक।
प्रेजेंट सर।
ओके, मोहम्मद खिजर अकरम। ठीक है, खिजर अकरम प्रेजेंट है। अच्छा, बुरहान अली खान। बुरहान अली खान। बुरहान अली खान एब्सेंट है। अच्छा, जैनब उमैर।
Present.
ताहिर हमीद प्रेजेंट है। सैयदा मायम फातिमा जैदी। सैयदा मायम फातिमा जैदी। मायम फातिमा जैदी एब्सेंट है। अच्छा, शमरेज तसव्वुर।
प्रेजेंट सर।
शमरेज तसव्वुर प्रेजेंट है। हसन आसिफ।
प्रेजेंट।
हसन आसिफ प्रेजेंट है। आयजा जफर।
Present, sir.
आयजा जफर प्रेजेंट है। फैजुर रहमान। फैजुर रहमान प्रेजेंट। बेटा, अपने माइक का कोई कुछ करें, माइक ठीक करें भाई अपना, क्योंकि फिर आगे जाके आपको, आप हर वेडनेसडे को होता है ना ये तो, हर क्लास सेमेस्टर के पहले वेडनेसडे को। फैजुर रहमान प्रेजेंट। अमीमा फरीद।
Present.
अमीमा फरीद प्रेजेंट है। मोहम्मद बिलाल खालिद प्रेजेंट है। हसन फैसल।
प्रेजेंट सर।
हसन फैसल प्रेजेंट है। और इब्तिसाम आबिद
प्रेजेंट सर।
प्रेजेंट है, ठीक है ना? तो यहाँ पे सेव
सर
कर
ये
लेते हैं।
उसामा।
जी।
सर उसामा बिन तारिक, मेरी सर उसामा बिन तारिक 009।
तो आप अभी आए, लेट आए हैं?
जी सर।
क्यों लेट क्यों आए?
सर मैसेज सीन अभी की है।
मैसेज सीन अभी नहीं करना था, जब आपको रात से मैंने बताया हुआ है आपके सीआर को कि भाई आपकी
सर ये
क्लास।
अटेंडेंस के मिडल में, सर अटेंडेंस के मिडल में, आप वो दरमियान में आ गया था, तो आप सबकी ले रहे थे तो आखिर में बताया।
चले ठीक है। अच्छा, ये हो गया आपका। अच्छा, ये आपकी अटेंडेंस हो गई। नाउ कमिंग टू द, हमारे पास अब आते हैं हम लोग दोबारा से लेक्चर की तरफ। अच्छा, ये तो आप लोगों को पता है ना, कल 2:30 से 4:30 आप लोगों की एवेल्यूएशन है, ठीक है ना? अच्छा, कमिंग टू द नेटवर्क लेयर राउटिंग, हमने यहाँ पे डिस्कस कर रहे थे, तो हम एक एक करके थोड़ा सा इसको रिवाइज करते हैं, उसके बाद फिर हम जो है वो अपने राउटिंग प्रोटोकॉल्स की तरफ जाते हैं। वी विल गो टुवर्ड्स द राउटिंग प्रोटोकॉल्स। हमने कल की क्लास के अंदर दो प्रोटोकॉल्स पढ़े थे ग्राफ थ्योरी के। दे वर ओपन शॉर्टेस्ट पाथ फर्स्ट, एंड द डाइक्स्ट्रास एल्गोरिथम, एंड द बेलमैन फोर्ड एल्गोरिथम। इन दो एल्गोरिथम्स की बेस के ऊपर हमारे बाकी एल्गोरिथम बेस करते हैं, इन दो चीज़ों के ऊपर, ठीक है ना। ठीक है ना। सो कमिंग टू द लेक्चर, तो ये हमारे पास ग्राफ हम देख रहे हैं कि ये पूरा कंप्यूटर नेटवर्क कैन बी मॉडल्ड एज अ ग्राफ। हमारे पास जितने भी राउटर्स हैं वो हम हमारे नोड्स बन जाते हैं, और हमारे जो लिंक्स हैं उसके बीच में दे बिकम एजेस। तो हमारे पास राउटिंग वगैरह हमने थोड़ा डिस्कस किया था कि कैसे जो है वो हमारे पास एक जगह से दूसरी जगह पे हम पैकेट्स भेजेंगे डिपेंडिंग ऑन देयर आईपी एड्रेसेस, ठीक है ना। अब ये टू फाइंड द बेस्ट रूट, द इंटरनेट कैन बी मॉडल्ड एज अ ग्राफ इज अ सेट ऑफ नोड्स एंड एजेस दैट कैन नॉट that connect the nodes. To model an internet as a graph, we can think of each router as a node and each network between a pair of routers as an edge. The internet is modeled as a weighted graph in which each edge is associated with a cost. In routing, the cost of an edge has different interpretation in different routing protocols. If there is no edge between the nodes, the cost is infinity. Okay, फाइन कि अगर हमारे पास दो नोड्स हैं, उसके दरम्यान में एज है ही नहीं, यानी कि हमारे पास कोई लाइन हमारे लगी हुई नहीं है, कोई लिंक ही नहीं है, तो इसका मतलब कॉस्ट इन्फिनिटी हो जाएगी। कॉस्ट क्या होगा? कॉस्ट कैन बी एनीथिंग। फॉर एग्जांपल हम ये कह सकते हैं एक सर्टेन कंडीशंस के अंदर कि हम कह सकते हैं कि बैंडविड्थ जो है वो बहुत अच्छी है किसी एक लिंक की। तो हम कहते हैं कि यार बैंडविड्थ बहुत अच्छी है, यानी इस लिंक की स्पीड बहुत ज़्यादा है, तो हम समझते हैं कि ये जो है वो बहुत अच्छा जो है वो एक लीस्ट कॉस्ट हमारे हमें हम जल्दी यहाँ से पैकेट पहुँच जाएगा। तो कॉस्ट इन टर्म्स ऑफ टाइम हमारे पास कम हो जाएगी। फिर हमारे पास ऐसा भी हो सकता है कि कोई लिंक जो है वो बहुत ज़्यादा क्या नाम है एक्सपेंसिव हो, क्योंकि जाहिर बात है अगर हम वो लेते हैं, सब्सक्रिप्शन लेते हैं वो मरीन केबल्स की, तो शायद वो कम उसके अंदर ज़्यादा स्पीड हमको मिल जाती है। अगर हम इंटरनेट को लेके लेके चलें थ्रू द सैटेलाइट लिंक, तो वो हो सकता है हमें ज़्यादा जो है वो कॉस्टली पड़े। तो वेट के कॉस्ट कैन बी एनीथिंग, ठीक है ना। तो इस केस के अंदर भी ऐसे ही होता है, हमारे पास इंटरनेट जो है वो ग्राफ है, और ये अगर आप देखें तो जो राउटर्स हमारे पास बने हुए हैं ABCDEFG, ये 7 नोड्स हैं, और वो किसी एक कॉन्फ़िगरेशन में कनेक्टेड है, और उनका आपस में जो है वो कॉस्ट हर लिंक के ऊपर हमने लिखी हुई है कि हर लिंक से पैकेट के जाने की कॉस्ट कितनी है। फॉर एग्जांपल ए से बी तक अगर पैकेट जाएगा तो उसकी कॉस्ट जो है वो हमारे पास 2 बनेगी। लेकिन अगर ये लिंक डाउन हो जाता है तो हमारे पास ऑल्टरनेट लिंक मौजूद है जिसके थ्रू कॉस्ट ज़्यादा होगी, लेकिन उसके थ्रू हम जा सकते हैं। लेकिन ऐसा भी हो सकता है हमारे पास, फॉर एग्जाम्पल सी से अगर हमें जाना है एफ के ऊपर, तो हमें 4 का लिंक डायरेक्ट मौजूद है, लेकिन हम जी के थ्रू भी 3 और 1 के थ्रू जा सकते हैं। तो कभी ऐसा होता है कि हमारे पास मल्टीपल एजेस जो होते हैं वो कम कॉस्ट बनाते हैं, और सिंगल एज का जो पाथ है हमारे पास वो ज़्यादा कॉस्ट का होता है। ऐसा भी हो सकता है हमारे पास, दिस कैन ऑल्सो हैपन, ठीक है ना। तो हमारे पास अब जो हम आते हैं, तो नेक्स्ट काम हम करते हैं, और वो ये है कि हमारे पास दिस इज द लीस्ट कॉस्ट राउटिंग। व्हेन द इंटरनेट इज मॉडल्ड एज अ वेटेड ग्राफ, वन ऑफ द वेज टू इंटरप्रेट द बेस्ट रूट इज टू फाइंड द लीस्ट कॉस्ट रूट बिटवीन सोर्स एंड डेस्टिनेशन अमंग ऑल पॉसिबल रूट्स। अब हम क्या करते हैं, हमने इन डाइक्स्ट्रास एल्गोरिथम वी फाउंड द शॉर्टेस्ट पाथ फ्रॉम वन नोड टू ऑल अदर नोड्स। So we can do this for all nodes, and we will be able to find the shortest path from all nodes to all other nodes. और in other words, हम ये कर सकते हैं कि हर नोड जो है वो अपने पास कैलकुलेट करे कि उस तक बेस्ट रूट कौन सा मतलब कौन सा शॉर्टेस्ट पाथ बनता है, ठीक है ना। The each router needs to find the least cost route between itself and all other routes to route a packet using the least cost criteria. ऑब्वियस सी बात है, अगर ए से लेके जी तक का लीस्ट कॉस्ट रूट ए पे कैलकुलेट होगा, तो ए उसको यूज कर सकता है आराम से कि पैकेट भेजने के लिए। द बेस्ट रूट बिटवीन ए एंड ई इज ए बी एंड ई, 2 + 4 विद द कॉस्ट ऑफ 6, राइट। 3 + 5 तो हमारे पास 8 हो जाएगा। और इसी तरीके से अगर हम बी से सी पे जाए, सी से एफ पे जाए, एफ से 2 पे जाए, तो वो और बड़ा लंबा कट हो जाएगा। So Bellman-Ford equation is used to find least cost between source and destination. तो Bellman-Ford algorithm हमारे पास least cost route के अंदर यूज होती है to find the least cost between source and destination. So several routing algorithms exist. One is the distance vector routing, the other one is the link state routing, and the third one is the path vector routing. अच्छा, distance vector routing and link state routing are algorithms that are within a network. If you have to send a network through an intra-domain, तो हम उसको फिर हम देखेंगे आगे कि हम पाथ फैक्टर राउटिंग हम उसमें यूज करते हैं. द डिफरेंस इज इन द वे दे इंटरप्रेट द लीस्ट कॉस्ट एंड द वे दे क्रिएट द लीस्ट कॉस्ट ट्री फॉर ईच नोड. अच्छा, दोनों अब ये एल्गोरिथम्स जो हैं, ये डिफरेंट एल्गोरिथम्स हैं. करते क्या है, दे फाइंड द लीस्ट कॉस्ट ट्री फॉर ईच नोड. So routing a protocols implement one of these algorithms. अच्छा, अब अगर हमें बस इंटर डोमेन में करना है हमें, इफ वी नो ऑल ऑफ द राउटर्स इन द नेटवर्क, we can use the routing information protocol or open shortest path first. And if we have inter-domain, for example, if we have to find a least cost path from this domain to any other domain in the world, then we have path vector algorithm. We are not going to be going to have we will not be going to into the detail of border gateway protocol, but BGP. But the idea is that we have to instead of calculating everything ourselves, we have to rely on the calculation of the router at the edge, at the border, to calculate that where to which place we can go in which cost, right? So that is essentially the difference. In the first one, in intra domain, we calculate all the paths ourselves, but in the inter domain we cannot calculate all the paths by ourselves. We have to trust the border, the router. So and that border router has to trust some other router in the internet for routing of packets. So in routing protocols, the routing protocol is a combination of rules and procedures that lets routers inform each other of changes. So in a routing protocol, we normally have a static network in which the links and connections are fixed. But when we start the network, we have to exchange the messages so that different routers know that which of the link in the network are active and which of the link in the network are not active. Also, if something goes wrong and a link goes down, then that news should travel to all the nodes in the network, that how that change is affecting the routing decisions in the network, right? Routing protocols are used to create and update routing tables. Each routing protocol is based on an algorithm. So as we said that the routing protocols are based on the shortest path algorithms that we discussed in the previous class. However, the routing protocol is more than an algorithm, where a protocol needs to define its domain of operation, the messages exchanged, the communication between the routers, and interaction with the protocols in other domains. For example, we can calculate the shortest path by exchanging the information between routes, but we have to find that what is the domain of our operation, in which part of the network are we going to calculate this, in what manner we are going to exchange the messages, the format of the message, the format of the protocol data units or the packets, and the communication between the routers and the protocols that are used in other domains. So a protocol is not a very is something that is built upon algorithms, right? So now that we know the details of detailed understanding of the algorithms, we can go further and understand the distance vector routing protocol. So in distance vector routing protocol, the least cost route between any two nodes is the route with the minimum distance. Okay, so each node maintains a table of minimum distances to every other node. Then the table at each node also guides the packet to the desired node by showing the next stop in the route. What we have in the table is the minimum distance from yourself to that node and the next hop through which that minimum distance is found. So each node shares its routing table with its immediate neighbors periodically. And when there is a change, initially the protocol will not converge. Initially it will take some time to converge. It will exchange messages about their links all over the network, and then it will just settle down. And after some time, there are packets that are shared with the neighboring nodes and forwarded to every other node to find the updates on the network, whether some link has changed, cost of some link has been increased, or cost of link at something, some cost at some link is decreased. Well, cost can be increased and decreased because we can have the load factor. If there is more load on a link, we can increase its cost. If we have less link, we can decrease its cost. Also, whenever a link is down or a router goes down, then there's a change in the network, then we have to update it. So there are two events. One is periodic event, and uh, one is the change at any point in time. Once the tables are shared and updated, the tables are stable where each node knows how to reach any other node and the cost. So once things are stabilized, each node knows how to reach any other node in the network and the cost of going towards the network. So at the beginning, the stable tables do not exist, where each node can know only the distance between itself and its immediate neighbors. That is, those neighbors that are directly connected to it. So for the moment, we assume that each node can send a message to the immediate neighbors and find the distance between itself and the neighbors. So for the moment, we can assume that each node can send a message to the immediate neighbor and find the distance between itself and those neighbors. The direct connection. So first, in the first phase, there is a direct connection between the neighbors, and they can be estimated. We can send a message to our neighbor, get a response, and find that what the cost of that link is. For example, if there is too much delay, we say that okay, cost is too much over here. If there is less delay, then there is difference. If we can know the bandwidth of the link, we can update our cost accordingly. The calculation of the cost is totally up to us, that whatever we want to do, we want to give equal cost to all the links and count the number of links, that is fine. We want to find the delay, that is also fine. We want to find the maximum delay on that link, that is also fine as a cost. We want to find the bandwidth of a link, that is also fine as a cost. We want to find the jitter or any other factor, or a combination of these: delay, jitter, bandwidth, and make a cost factor. That is all up to us, but the algorithm will depend on the cost that we give it for each link. So in the distance vector routing, this is the initialization. So over here we see that there is a network A, B, C, D, and E, and we have links connected to each of these neighbors, and on each link we have cost associated with it. So what we do is that we at A we have the routing table. We see the routing table at A and try to understand it. So at A, A is connected to three links: B, C, and D. From A to cost from going from A to A is 0. From, of course, we don't have to go anywhere. Cost from going from A to B is 5, because there is a one link that has cost is equal to 5. The cost of going from A to C is true with this direct link. Cost of going from A to D is 3 based on this direct link. And cost of going from A to E is infinity, because E is not the neighbor of A. So it cannot send a direct message to A. A cannot send a direct message to E. Similarly, we see over here that we have A, from A we have from B we have cost going to A equal to 5. We have cost going to B equal to 0, because we already are at 0 at B. Cost from going to from B to C is 4. we have a direct link with cost is equal to 4. Cost from going from B to D is infinity because we cannot go directly initially. We don't have a direct connection from going from B to D. So we write infinity over here. And cost for going towards E is 3 because we have a direct link with E. Similarly, we have this table at node D. At node D, from cost for going to A is 3 that because it's a direct link. We have no other direct link from D to any other node. So cost of going to B will be infinity initially because it won't know that whether there is a path that exists from or in going to B. And cost for going to C is infinity because D doesn't know whether it can move towards C or not. And cost from going to from D to D is 0 because it's already there. Cost from going from D to E is infinity because it doesn't know whether it can reach E or not. So D is blind about everything else except for this link with A. Similarly, we have node C. At node C, we have cost from going to node A is equal to 2 because there is a link with capacity 2 with cost 2. Okay. From C, we have we can go to B with cost is equal to 4. There is a link that is cost is equal to 4 going from C to B. Going from C to C, we do not have any cost because we are already at C. C does not know whether it will be able to get to D. So it will write infinity because it's not a direct neighbor. Going to E, we have a link that is that has weight that is cost is equal to 4. So it will write the cost is equal to 4. That is C stable. Similarly, E. Cost of going to A is infinity because there is no direct link. There are direct links with B and C. We can go to B with 3 cost. We can go to C with 4 cost. And we cannot go directly to D because it doesn't know whether there is a path that exists. After it will get some information from A, C or B about D, it will not know whether it can reach D or not. Okay. So E is 0. Obviously E is going to be 0 because it is already at E. So the next part, the next column is all blank over here because initially the next column is always going to be blank. Why is it? Because if we have a path from a node to any other node, we write the cost of that path, that is a single link path, and we go directly to that node. For example, from A to B, we go directly with this link. So we do not go through any other node. So we write blank over here. So all entries of next will be blank because all nodes are going either directly towards the node, destination node, or they will not be going towards the destination node. For example, although this is a connected graph, but D cannot go directly towards E. It will need at least 3 edges as we see. So coming along, now we will be able to understand that what goes further. So in distance vector routing, we have sharing and updating of routing tables. A node shares only the first 2 columns of its table to the neighbor. Only the first 2 columns are shared. The third column is not shared. The third column can easily be deduced. For example, if A shares its first 2 columns with D, D can update its routing table. It can say that okay, I can get to A in 3. Okay, I can get to B through A. in 3 plus 5 because over here it's 5. I can get to C with 3 plus 2 because over here we have 2. I can get to D with 3 plus 3, but I'm already there with 0, so I need not update this. And I cannot get to E. So in all three cases, it will write in all, in case of A, it goes directly. In case of E, it doesn't go anywhere. In case of D, it is at D already. So wherever it will update these two columns. And it will write the next node as A over here. Similarly, wherever there is an update, we will update the next column. So updating text takes 3 steps. The receiving node needs to add the cost between itself and the sending node to each value in the second column of the received table. The receiving node needs to add the cost between itself and the sending node. to each value in the second column of the received table. The receiving node needs to add the name of the sending node to each row as the third column. So whatever we get from A, we have to add this 3 into it and see whether the result is better or not. If the result is better, then we have a better route from A and we write A over with that, right? So the third thing is that the receiving node needs to compare each row of its old table with corresponding row of modified version of received table. Okay, the receiving node needs to compare each row of its old table with corresponding row of modified version of the received table. So if the modified version is better, it will go towards the modified version. Otherwise, it will remain. It will retain the previous version. If the next node entry is different, the receiving node chooses the row with smaller cost. If there is a tie in the cost, old entry is kept. Okay, so if next node entry is different, the receiving node chooses the row with smaller cost, and if there's a tie, old entry is kept. If the next node entry is same, the receiving node chooses the new row. So if next node entry is, for example, if A has found that it has got a better path towards, it has found a better path towards B, a least cost path. For example, this is 2, this is 1. If it finds that 2 plus 1 is equal to 3, this is a better path. So it will send the new entry with B is equal to 3 to D. So now D will know that the next node entry is same, but the receiving node chooses the new row. But the entry that the cost has decreased. So it will choose the new row. But if the next node entry is different, then the node chooses the row with smaller cost. In case of same, it will just keep the old entry. So in a short time, if there is no change in the network, each node reaches a stable condition in which contents of its tables remain the same. In a short time, if there is no change in the network, for example, if there is no change in the network in the short time, each node reaches a stable condition in which contents of its table remain the same. Okay. So when the table is stabilized, then we have a stable condition, and then we will give the periodic update messages or news over the network. So in distance vector routing from A to C, the only benefit from updating of node A is the last entry, that is how to reach E. So at A we receive a table, C is table. This is 240 infinity and 4. This is C is table. We receive at A. So now we know that at A the value is 2 over here. The link between A and C is 2. So we will add this 2 into this. So whatever we do is that this is the A's modified table. We getting cost to A is 4 now, because we add 2, link 2 over in the cost from going to C is 2, so we add 2 in all the entries. 0 plus 2, infinity plus 2 is infinity, 4 plus 2 is 6, and we add C as the next node. And then we compare with what? A's old table. This is the old table of A, 0, 5, 2, 3, infinity. This is the old table of A, 0, 5, 2, 3, and infinity. So we compare it with this, and we see that if let's see what is over here. If next node entry is different, then we choose with the smaller cost. Okay, if there is a tie, we keep the old entry. So we choose the with the smaller cost. This is the smaller cost, so we choose A0, this row. Okay, so next node entry is different. Now over here, the next node entry is different in case of B, but this one is smaller, so we keep B. So we keep this entry that is smaller. Next node is C, that is equal to 2. Over here, there is a tie, so we keep the old one. Over here, the next node entry is